Okay, good morning to everyone. I'm honored to be here. I'm Dr. Kamal De, Associate Professor in Applied Chemistry and Chemical Engineering, University of Chicago. And my co-authors, Dr. Suman Ganguly from the same department and same university, and Professor Benu Kumar De, Pro Vice Chancellor and Professor in Chemistry at the University of Chicago, and Professor Lucina Saturday. She is a renowned professor from University of Brescia, Italy. And my title, Sustainable Synthesis of Hydrogel Scaffold for Tissue Engineering and Regenerative Medicine. And I would like to say this field is very new in Bangladesh because I work on human stem cell. So why we need to focus on this field? If you go the present scenario, you can see by 2050, the world will be home to 10 billion people. And 2 in 5 of these people will be aged 60 or over. And 434 million over 8 years old. So it will create a great challenges over our healthcare system. And present clinical approaches are not enough to meet a significant number of clinical disorder due to disease, trauma, congenital abnormalities, and aging. What the present clinicians do, they only manage patient symptoms using medication or devices. So we need something new. Here's the beauty of tissue engineering and regenerative medicine. Here you can see, this is actually the fourth industrial revolution, fundamentally changing the way we live, work, and relate to one another. As the present clinical approach is not enough to cope with the abnormalities, and this is what we are doing now, we must consider this thing, tissue regeneration. And why? This one, we can regenerate damaged or disordered tissue using a lot of technique. You can see we can use adult stem cells, and we can do in situ regeneration using bioscaffold. We can do stem cell therapies. We can, using pluripotent stem cell, we can make organoid as well as interspecies chimeras. In my topic, I will talk about this in situ regeneration of tissue. Okay. Now we'll talk about the tissue engineering. What's the challenges and opportunities? Every year, thousands of patients die while waiting for an organ transplant due to the paucity of donor organ. And the aim of tissue engineering is to restore form and function of diseased, damaged, and lost tissue or organ. In tissue engineering, there are three pillars: cells, scaffold, and signal. And in every sector, there are a lot of challenges associated with cell technology. It means what would be the sources of cell production, as well as construct technology, manufacturing technology, and FDA approval. I will talk about these two challenges, construct technology and manufacturing technology. Here, the role of a scaffold in tissue engineering. What's the function of a scaffold? Actually, it's a home for biological cells as well as signaling molecules. And then this scaffold guide stem cell toward the specific organ or tissue regeneration. It's a very nice thing. And I will talk about how the scaffold guide stem cell to a specific tissue formation. Here, when we talk about the ideal tissue engineered scaffold, we have to consider a lot of parameters. You can see biocompatibility, degradability, structural stability, bioresorbability, cost effective, scalability, easy processable, customizable, goods, a lot of parameters we have to consider. And in my research, I consider all of these parameters. Selection of a scaffold. We select the hydrogels. There are a lot of biomaterials we can use as a scaffold. Why hydrogels? The beauty of hydrogels is that we can, we can use hydrogel, we can fabricate hydrogel in any size, shape, and form, you can see. And hydrogel is very similar to our natural tissue. But hydrogel has many limitations. They are usually mechanically weak, difficult in sterilization, and can be hard to handle. Still now is a critical engineering challenge to design clinically relevant hydrogel scaffold in a congenial and sustainable approach. So that's why my aim of research is rational design and development of tailorable, simple, but robust synthesis process of producing cross-linked hydrogen scaffold for tissue engineering application. And I will talk about how the constituent of hydrogels and viscoelastic properties guide, stimulate the stem cell function. Here the methodology, this is the novel hydrogen synthesis. Here you can see we adopted 4 steps: liquid phase cross-linking and grafting here, and unidirectional freezing, and then freeze drying and post curing. We have to apply all this process. Then we have found out this is the hydrogel, this is dried hydrogel, and this is wet hydrogel. You can see it's very highly porous network. Here, what about the chemistry? Cross-linking reaction. You can see we use this cross-linker, polyethylene glycol diglycosidiol. It's just 2 beauty. It is the epoxy oxide. This epoxy group, during reaction, this group actually open up and then react with the available functional group of gelatin, such as ammonia, and then form the carbon nitrogen stable network. You can see gel-packed network after cross-linking. Okay, what's the versatility of novel hydrogel synthesis? This is very true in tissue engineering, regenerative medicine. One size fits all strategy is unrealistic in the context of designing scaffold, because in our body, all tissue is unique, all organs are unique. So we can, in our synthesis protocol, we can adopt, we can add many natural polymers as well, synthetic polymers, as well as nanomaterials. You can see we can use this all of polysaccharide, and we can use also the nanomaterials. All materials have some advantages and disadvantages. We can make high-fit multi-component hydrogels. Here's the salient features of synthesis protocol. It's very green. We make the hydrogen aqueous media, no catalyst, no acid is involved here. And simplicity is a very simple process. Versatility, we can accommodate a lot of polymers and nanomaterials. Sterilizability is very important. When we use something for making tissue, it should be sterilizable. And customizability, we can customize as part making our target tissue. You can see we can make hole, we can make ring, we can make a cylinder, and so on. And scalability, it's scalable. We can scalable the synthesis protocol for clinical application for manufacturing. And 3D printability, you know, this thing, additive manufacturing is now coming. Is booming, and with our synthesis protocol, we can use this 3D printing for making for precise structure, and we can actually drill hydrogel. Yeah, you can imagine hydrogel is very soft, so we can even dry condition, we can drill it for making hole. Here you can see the table. It a set of hydrogels we produced, and swelling ratio is this more than 500, and porosity is higher porosity. Porosity is important because when we seeded cells, we need to supply nutrient. So porosity and channel works like to carry the nutrient to the cells, otherwise cells will dry. Here we do the surface morphology using both optical and SEM. You can see the very porous network, and the pore size ranges 20 to 400 micron. Here's the sterilization, because when we apply this 25 kilogram sterilization, it's a typical sterilization technique for healthcare products. You say that the mechanical properties and physical properties, it doesn't sense. That means these materials can be effectively sterilized using the commercially available sterilization technique. It's a very good thing, so that the process can be utilized as a commercial scale. Here, maybe mechanics matter the most. When we talk about cells, cells is actually mechanical stuff. And there you can see a lot of mechanical properties such as viscoplasticity, viscoelasticity, gradient stiffness, bulk stiffness, mechanical memory, mechanical confinement, mechanical anisotropy, non-linear elasticity, mechanical force. All these mechanical clues actually guide the mechanical stem cell towards a specific tissue. Here, this is my review article in RSC journals avoiding this thing, how mechanical is the progress in the mechanical modulation of cell function in tissue engineering, how mechanical cues actually stimulate the stem cell to form the specific tissue. Here we produce anisotropic mechanical properties. What does anisotropic means? You can see when we compress our hydrogels in two directions, parallel and perpendicular, we have two different mechanical properties. Here we can see gelatin packed hydrogen. We have also anisotropic properties. But when we use hydroxyethyl cellulose, we have the isotropic. In parallel and perpendicular, we have the same, because this is due to the higher hydrophilicity of hydroxyethyl cellulose. In this case, we use the carbon black, quadratic carbon black. Here is a carbon black 1, that means 10%, 15%, and 20%. When we use 10% carbon black, we have the anisotropic mechanic. When we use 15%, it's intermediate one. When we use 20%, then it becomes isotropic. That means this anisotropy is governed by materials, nanomaterials, as well as composition. Here you can see, due to the anisotropy, the microscopy, this visualization of anisotropic diffusion is different due to the anisotropic structure. Here you can see the ratio of anisotropic ratio. We have the gel packed hydrogen have the highest anisotropic ratio. Why we important this anisotropic mechanics? If you go to our cardiac tissue, you have see they are structurally anisotropic and mechanically anisotropic. And when we produced our hydrogel, they have also structurally and mechanical anisotropic. So biomimetics is important. When we use tissue using stem cell, we have to actually biomimetic of the specific tissue. Now here you can see mechanical properties of nanomaterial reinforced hydrogel. When you use nanomaterials, mechanical properties actually increased many folds. It's important. Okay, here in cyclic compressive mechanical properties, you can see there is actually video. You can see this hydrogels actually shape recover. We can compress around 90%. It's recovered its original position. It's a before compression and after compression. And mechanical stability, you can see in cyclic compressions, we can see this mechanical stable, and its fatigue resistance actually increase. You can see this video is compressed 90%, but we keep it actually again recover its original shape.
Did you download the movies last time?
Maybe I can stop here. I can go.
Yeah.
Okay. Okay. Now this is important stress relaxation properties, viscoelasticity. Our hydrogel system actually shows viscoelastic properties. You can see, or hydrogel actually shows the stress relaxation over time. It's both in original in initial stage as well as during hydrolytic degradation. This shows the viscoelastic properties. Why this is important? Our tissues are viscoelastic. So when we make hydrogel, it should be viscoelastic. And gelatin packed chitin 2, which is actually 16% chitin, this hydrogel shows the highest, this blue line, highest and fastest stress relaxation. Okay, here now I will show how can we use this hydrogel for making bone tissue. Here stem cell differentiation performance. You can see here, we use our hydrogel and we use the human bone derived stem cells. You can see after 20 days, this stem cell actually produces the minerals. Mineralization is here, and stem cells actually turn to osteogenic. You can see osteodifferentiation and mineralization happen after 21 days. So we can make bone tissue using a stem cell and materials. This is the beauty of this work. And here you can see, using same material, we can do chondrogenic differentiation of human mesenchymal stem cell. Why chondrogenic differentiation? You all know this osteoarthritis. Why it's happened? Hey, about 40 years, everybody has more or some or less osteoarthritis. This is due to the degeneration of cartilage. And our body cannot heal it automatically. So we need to support it. Here you can see, when we use our hydrogel system and use the human bone derived mesenchymal stem cell, you can see here when chitin concentration is higher, 16%, then we have actually type 2 collagen. Type 2 collagen is important because this is the type 2 collagen. This is the stable chondrogenesis. When we have the type 1 or type 10, then this is the fragile fibrotic chondrogenesis. This fibrotic chondrogenesis means this will lead to osteoarthritis. So this is very nice thing. We can use our hydrogel system to treat this osteoarthritis. We can regenerate cartilage. Here you can also see the chondrogenic differentiation. This is the immunohistochemical evaluation of chondrogenic, fibrotic, and hypertrophic marker. You can see this red one actually fibrotic and hypertrophic marker. Here you can see this gel packed chitosan 2 only you have some dotted, red dotted. Then this is phenotypically stable. That means this is the good one. And this gelatin packed chitosan 2. This is very good one. We can treat osteoarthritis using this hydrogel system. And here, future working collaboration with the University of Brescia, University of Glasgow, and University of Toronto, Canada. We are doing mending broken heart. You know now, heart failure is like a pandemic. We can make heart, as well as nerve regeneration. We can regenerate a nerve using this hydrogel and using a stem cell. Also in our department, we are doing hydrogel for drug delivery, as well as hydrogels for environmental remediation. We can do this. And concluding remarks, this developed synthesis strategy is really nice for tissue regeneration. It has a lot of very fantastic characteristics, which is suitable for tissue regeneration. Here, this is the reference. All of this actually published in very renowned journal, high impact journal. And here, thank you for your kind attention. And actually we already applied patent application of this process because I believe in innovation, not imitation. And we already applied this synthesis, this novel, and patent application number is actually missing due to this maybe figure. Thank you very much for your kind patience. If you have any question, I'd be pleased to answer.
Thank you. So, can you ask any question, please? No. So, Kamal, thank you very much.